Hello everyone, good to see you all in number here. So today we have our own Professor Antonio Bianchi. He's a faculty member and associate professor in computer science department, where he's part of the Purdue security lab, PERSEC lab, and he works on mobile security in particular, but anything that involving system security is of his interest. Without further ado, Antonio.
Okay, thank you. Is it good? Should be good now. Yes, so thank you for the introduction. Yeah, my name is Antonio Bianchi. I will present a few projects related to, in general, software security, but in particular, how can we use LLMs to solve or help solving some software security tasks. So just about myself, one slide. My research interests are like mobile security, but more generally software security, system security, program analysis, and I'm also I teach software security, and I'm also I'm the advisor of the Boilers Purdue CTF team. And so I'm part of a lab, PureSec lab, with other 3 professors, and we do all sorts of research in the area of again, software security, system security. We have about 20 PhD students, and maybe the entire group is maybe around 30 students in general. This is one picture of us. This is another picture of us. And I mean, in general, if you are interested in joining us, you can send me an email, and then we can discuss if there is something you can do to help us in some of our research. Okay, so this is enough for the introduction. So what are we going to talk today? So as I mentioned, attacking and defending modern softwares with LLMs. I'm not a machine learning expert. I'm not an LLM expert, but recently, of course, everyone is trying to use LLMs to do different things. So here I'm just giving you some examples of how we have been using LLMs to help us, assist us in a few tasks related to software security. And in particular, I will cover 2 things. One is studying and developing exploits for the Linux kernel, and one is uncovering bugs in Rust's unsafe code. Okay, so the first kind of 2 projects I want to mention, they are part of this DARPA-sponsored project called DARPA Ingots. And the general goal is to automate how exploits and exploit chains against Android devices are developed or adapted to new versions. And also kind of determine whether a given Android device is exploitable or is vulnerable against some attacks or is not vulnerable, right? So this is the overall overall goal of the DARPA project. But so let's look kind of maybe one slide of background about what are we talking about here. So in Android specifically, what you might have the situation in which an application is malicious. Maybe it's a pretend to be a funny game, but in reality there is some malicious code running there. And this malicious code can potentially exploit one bug that is running, one bug of the running Android kernel, and use this bug to get code execution, to kind of influence the Android kernel underlining all the running Android apps, and then use this to, usually what is done is to get root. That means to spawn a new process that has root privileges, that can do anything on the system, and that is controlled by the attacker. And so this is an example. Things can even be worse. You might even have maybe an attacker over the internet try to somehow compromise an app running on the phone through an exploit, through a vulnerability present in the app, and then get control over the app, and then from the app trying to get control over the kernel through a vulnerability affecting the kernel. And this will be an exploit chain, in which you have a first exploit and then you have a second exploit, and you chain them together. So so in this area, I will mention two projects we have been working on. These are kind of work in progress. These are not like finished projects, but just give you a few ideas of how we can use LLMs to help with this. So the first one is exploiting exploitation primitives analysis. So basically, we have a lot of existing automated approaches. Typically, it's called fuzzing. And the idea is to automatically generate inputs, like sequence of system calls in this case, sending them to the Android kernel and see if it crashes. So this is a way that has been shown to be effective to just find vulnerabilities affecting the Android kernel and also the Linux kernel, because Android kernel is actually based on the Linux kernel. And also the idea here is that the crash is normally a symptom, in a sense, of a bug within the kernel, and then this bug might or might not be exploitable. So so what you get from a fuzzer, you get something like this. This is a list of 3 system calls with some arguments, and the fuzzer tried many different combinations of system calls and randomly found that these 3 system calls with these arguments makes the kernel crash. And once you have the kernel crashing, you're going to get something like this, and maybe you have seen it if you use Linux. This is a kind of a stack trace that basically is telling you, okay, the kernel crashed at this instruction, and it's telling you what was the kernel doing when it crashed. But of course, what is going on here? Like, it's hard because you just see a bunch of lines of code, not much information. So what is the bug? What is the root cause of this crash? What is the bug here? Is this bug even exploitable or not? If you want to try to fix this bug, where should you look into, right? So the stack trace is not very informative. And of course, what you could do, you can go through all these files, all these source code files mentioned here, analyze probably 10,000 lines of C code and trying to understand why a crash happened. But what can we do something to maybe help security researchers in doing this? So what we would like to do is basically, given a crash from a fuzzer, understand if and how it can be used to exploit the target kernel. And so here we have the crash. So we would like to understand what is actually the bug causing the crash, and then understand how this bug can be used as part of an exploit, as a component of an exploit, and then eventually see if we can put together different components and create kind of an exploit for the kernel. So, okay, so what we do in our approach is that we start from crashes found by existing fuzzers. Specifically, there is a fuzzer called Sysbot that is running automatically, I think, from Google. And so they are taking care of that. And they reporting crashes. And then we extract information regarding the input crash in the kernel, like the sequence of system calls that trigger it. We extract information regarding the kernel code that actually crashed. All those lines of code, we go through them automatically. We detect any piece of code related with any function involved with a crash. We record the state of global variables at the moment of crashing. We check all the branches that determine whether or not the vulnerable location is reached, determine what is being checked, and then we provide all this information to an LLM by using a prompt like this. Of course, I'm not going to go through the entire prompt, but just to give you an idea. So basically, we tell the prompt, this is the crash log. These are the snippets of code that are relevant to it. Provide us information about how to reach this crash, what is the root cause. And also we provide kind of the format of how we want the output from the LLM to be. And also we pass a kind of detailed list of requirements about things that we want the LLM to do, things that we don't want the LLM to do. So that's what we do. I saw a raise hand. Should I answer now? I saw a message on Zoom about someone raise hand, or maybe we answer questions at the end. Yeah. Up to you. Okay. Well, at the end I can answer all questions. Okay. So and what our tool returns is information regarding if and how the exploit to exploit the analyzed crash, and some short summary of what is the root cause of the vulnerability. And so instead of getting something like this, now we use the LLM to obtain something like this, which is at least more understandable than this. And so basically says, okay, what's going on here? It tells us a craft inode in the file system with some invalid data, triggers an error path within the code that eventually can lead to a use after free. So of course, you still need to be a little bit expert about these things to really understand what's going on, but it's much better than trying to just check the stack trace. And it also tells us some sort of precondition, things that you need to do in order for this bug to be triggerable. And of course, again, this can be used both in an offensive side, like if you want to develop an exploit and you want to, this can help you in understanding how to develop an exploit, but also from the defensive side, like you got a crash, you want to understand really what is going on and potentially patch it, right? Okay, kind of in the similar area, there is another project we have been working on that is, so let's say, so there are people that have developed these exploits for the Android kernels. If you look at any of them, it's very complex. It's like maybe more than 1,000 lines of C. So, and it contains a lot of hard-coded values that are tailored against a specific kernel version and a specific Android device. But typically that kernel exploit might also working against other different versions and other devices, but in all these different constants within it, they needs to be kind of modified. But this sort of fine-tuning of an exploit, it's very laborious, requires a lot of knowledge about what's going on in the kernel, so it's definitely not easy, especially because small kernel variation can cause an exploit to stop working, even though the underlying vulnerability remains present. And so this could be a problem even from a defensive point of view, in which you are the manufacturer of an Android device, you want to know if you are affected by a given exploit, you try it, it doesn't work, but maybe it doesn't work just because the vulnerability is still there, but just because it needs some small adaptation, but you don't know how actually to do it. So can we kind of have this sort of automated exploit adaptation? And what can we do in this area? So as I mentioned, this can have offensive application, of course, reduce the time required to develop a working exploit for a new kernel version, but also defensive application to determine whether a given device is vulnerable against a particular exploit, and potentially then patch it, hopefully. So in this case, we use LLMs to find exploit values that need updating for a new kernel versions, and then we use Ghidra to detect the correct values for these constants in the target kernel. So for instance, these are just a few lines from a maybe 2,000 lines of C exploit, and then the LLMs can help us, suggesting us that maybe these values they need to be adapted for the new kernel, for a new kernel version, and then we use kind of static analysis. We analyze the target kernel and we try to understand corresponding values in the target kernel. And so here I'm showing you an example of, I'm showing you parts of the prompt we use with LLM. So we say you are a model which analyzes exploits for the Linux kernels, and these exploit depends on some offset and struct fields. You should identify these values within the exploit. And then again, we need to be kind of precise in what sort of data we are going to give to the LLM. So we define this in the prompt, and we also want to have, we tell the LLM precisely which sort of data we want to get out of it. So to summarize the two projects I mentioned, or kind of focusing on the LLM part here, I think there are, at least for us, a couple of lessons learned on how to use LLMs to do this sort of things, or to help with these sort of tasks. And one, I guess, is it is important to provide LLM with examples of data to be processed and the corresponding expected results. So this is something we definitely do, and it's something that it seems quite important. And also it's important to specify to the LLM what you do not want from it. So sometimes the LLM tries to be creative, or because sometimes the LLM doesn't really understand what you want it to do, and so it just outputs something that doesn't make too much sense. So it's important to specify what you do not want from the LLM. LLM can be used to perform this sort of fuzzy parsing scenarios in which we give them a bunch of snippets of code that is not compilable code, like it's just a bunch of snippets of code, but LLM can kind of understand what is going on without the because maybe other approaches requires you to compile the entire code and then apply analysis over it. These are more the traditional static analysis approaches. Whereas with the LLM, you just pass a bunch of snippets of code, and the LLM can try to understand, at least at a high level, what is happening. And of course, there are context window length limitations. Like, we cannot pass the entire Linux kernel to the LLM and say, okay, figure out where the bug is, right? And I think from our experience, the problem is also deeper than that, is that the more code you pass, or the more irrelevant code you pass, the more the LLM will kind of get distracted analyzing things that are not very relevant. So one good approach is that to use kind of a preliminary analysis, static analysis of the code to determine useful code locations, or to determine locations in which the LLM should be focusing on, and then only pass those to the LLM. Okay, so another project we have been working on recently, this is actually something that is going to be published in a conference in a few months, is DeepSurf. Then is about detecting vulnerability in Rust through fuzzing and LLMs. And here we are talking about Rust code, so it's not exactly the Linux kernel, but definitely there is a relationship here. And the fact is that many vulnerabilities are caused by memory safety issues, including most of the vulnerability used to exploit the Android and Linux kernel. So these memory safety issues have been around since forever, I guess, and people know about this problem. People have started maybe 20, 30 years ago, try to find a definitive solution against memory safety issues, but things are not that easy. And of course, if you write code in C, like most of the Linux kernel code, then you can have memory safety problems. So what a solution for memory safety would be to have a language that is both low level enough to allow system programming, to allow efficient code, to allow writing pieces of the operating system kernel, but also high level enough to avoid memory safety issues. And we do have such a language, or at least a solution that has been proposed to this problem is to use Rust, which is kind of a low-level language, but it guarantees memory safety. So indeed, the Rust was designed to combine memory safety and performance in computer systems, and it does so by enforcing mostly at compile time, but sometimes also at runtime, it enforces a lot of properties, and it performs a lot of checks to prevent memory safety problems. And so this is about Rust. And so you think, okay, now if I write everything in Rust, my code will be safe. However, this is not fully true, because Rust allows unsafe code. So you need to explicitly mark some code locations as unsafe, and within those code locations, Rust does not do its normal checks, and so you can have memory unsafe code within those code locations. And this is used, for instance, for interfacing with the native code or hardware interfaces when you need to precisely define, for instance, memory allocations, and also for performance reasons. Unfortunately, incorrect use of unsafe Rust code can introduce memory corruption. And so here I'm just showing you how unsafe code looks like. So you can have a function, and then you can have an unsafe block within that function, or you can have an entire function declared as unsafe, and then if you want to use this entire unsafe function, then you need to encapsulate the function call within an unsafe block. Okay, so in a sense, the use of unsafe code is governed by some sort of safety contract, let's say. That means that when you use unsafe code, let's say that you are a library developer and you use some unsafe code, then you are responsible to introduce manually all those checks that guarantee that that code does not contain memory corruption. So that's what you need to do. Unless you define an API as unsafe itself, and then if the API is unsafe, then whoever is using it knows that it's unsafe and it needs to be careful about its usage. But otherwise, is the responsibility of if you have a safe API encapsulating unsafe code, is the responsibility of the API developer is responsible to verify that unsafe code does not cause memory corruption. And I'm talking about libraries because a lot of Rust code is distributed through libraries. These are called Rust crates. So if you want to analyze analyzing all these Rust crates, it's very useful to potentially find bugs in code used in the wild. Okay, so I mentioned fuzzing before. I'm gonna just have another kind of background slide to point out a few things about fuzzing. So as I mentioned before, fuzzing is an automated form of dynamic analysis in which you run the code, you run a program repeatedly with a large number of generated inputs, and you monitor the code for crashes under the assumption that the crash is somehow a symptom of a bug that could be potentially exploitable. And so fuzzing typically works in a loop in which you generate some inputs, the fuzzer generates some inputs for the program, run the program with those inputs, monitor it from crashes, but also collecting code coverage information. And then the idea is that inputs that explore a lot of code are kind of good inputs that can potentially explore more code and find more bugs. And so these good inputs, according to some metric, are then used as template to generate new inputs in an attempt to explore more and more code and to achieve higher and higher code coverage and potentially find more and more bugs. So this is how fuzzing works in general. If you want to apply this to Rust, and especially if you want to apply this to Rust to find memory safety bugs caused by unsafe Rust code, there are some challenges, which I'm listing here. So basically, fuzzing a Rust library requires generating a harness. What is a harness? A harness is just a piece of code that converts whatever the input the fuzzer is giving you, which is just typically a list of bytes, into something that the fuzz library can process. So you need to convert these random bytes produced by the fuzzer into a sequence of library calls. And the harness is a piece of code that does so. So in case of Rust, the harness needs to use fuzzing input to generate a random sequence of API calls with randomly generated Rust arguments. Writing these, of course, you can write these Rust harnesses manually, and people have done it, but in our project, we wanted to do this automatically. And generating these Rust harnesses automatically it's kind of already a hard task for C and C++. In Rust, it's even more complicated due to the kind of the complex type system and language-specific features of Rust. Okay, so let's go through kind of these challenges more precisely. So as I mentioned, we want to target unsafe code within a Rust library. So first of all, we need to understand what are those APIs that can reach unsafe code, and then we want to fuzz them to potentially trigger some memory corruption. So we need to implement some sort of analysis, some sort of static analysis on the library code to identify APIs that can reach unsafe code, and to do this, you need to take into account Rust-specific control flow operations. You need to kind of basically build a call graph of how the different functions call each other, and within this graph, doing some sort of reachability analysis to see from which APIs you can reach the unsafe code. And this is something we implemented as modifications of the original Rust compilers. Then, you want to do library calls. So these are library functions that takes arguments. These arguments, they have types, but they can have complex types, like in a sense, the similar things of complex data structures in C. So, but to build these complex types automatically, to generate code that can build these complex types automatically is not that easy due to the complex type system of Rust, and also because in Rust there are not explicitly marked constructors. So you kind of need to, your automated approach needs to figure out which methods can be used as constructor to get back an object of one of these complex types and then pass it to the function you want to fuzz. Also, other complications. So there are function libraries that takes as an argument almost like a callback or a function pointer. So you pass as an argument another function. And then this other function is user-defined code, but you want to test this during your fuzzing process, because sometimes it's the presence of this user-defined code that actually cause bugs. So you want to test it, but of course you need to have a way to automatically generate this user-defined code, which is then passed as an argument to the function you want to fuzz. And yeah, and also sequences. So if you think about that, let's say you have a library function that is inserting an element to a list, and you know that that function is using some unsafe code, so potentially you want to test it. But most likely, if you have a function to insert an element into a list, you probably also have a function maybe to create an element or a function to delete an element. So it makes a lot of sense that your harness is not just testing a single library function separately, but it combines them together according to their semantic, according to the fact that if you have a list, it makes sense to first create it, then maybe add some element, then maybe delete some element, maybe resize the list. So these are all operations that make sense to do them together in a certain order. And of course, we want to automatically generate harnesses which follows these sequences of APIs. So how can we do this? So for instance, this is an example in which we have a bug that in order to trigger this bug, you need to, I think you need to create this object, and then you need to insert two data structure, and then you need to remove another object. So exposing this bug requires insertion of at least two items in the slab before removing the first. And so your harness should be able to do this. And so we call this sort of situation, we say that these three different APIs are semantically relevant. Okay, so this is the general approach, kind of an overview of our approach. So the first thing we do is, okay, let me go back. The first things we do is we do unsafe reachability analysis. So we want to understand what are those APIs that can potentially reach unsafe Rust code. Then we do an argument analysis to understand how to generate arguments for those APIs. Then we automatically generate a harness using, let's say, traditional program analysis. And then we ask the LLM to improve this harness and make it more, let's say, semantically rich. And then using this harness, we do fuzzing and we look for memory bugs. So let's go through kind of a few steps. So the static analysis. So the static analysis is built inside the Rust compiler. And what we do kind of a reachability analysis on the intermediate representation used by the Rust compilers to identify unsafe blocks, and then performing kind of a graph exploration to determine which APIs can potentially reach those unsafe code blocks. For the argument analysis, we need to use the Rust type checker to understand the type for each argument, and then to understand how to build such a variable of such a type. For instance, let's say here, let's say that we want to fuzz the function foo. So to be able to call this function, so this function takes as an argument a shape and an item, but the shape is of type shape, and the item is of type T, which is actually a trait, something like more like a Java interface. And then this is the definition of what a shape is and what the trait A is. So if we want to create these two arguments, in our harness, we need to kind of understand how to do it. So basically, we start from the function, we go into its arguments, and then we want to understand the shape. Is something that we can create by calling new, which is a kind of a constructor of a shape variable. And then we can also call this other method 0. And then this item of implementing the trait A, we need to, like, it has a trait function called describe, and then I guess it returns it returns, yeah, it has, I guess it has a reference to itself inside. So this is all information we need to know in order to then create something like this, which is a harness that takes fuzzer input and uses it to generate the variable t0, the variable t6 that are passed to the function foo that we want to fuzz. And so all this code needs to be kind of automatically, all this code is automatically generated by our static analysis system. Okay, so, but then, as I mentioned, we also want to improve the generated harness by using LLMs. And there are many reasons, but here I'm listing some of the reasons why this makes sense to do. So one reason is that statically generated harnesses do not support sequences. This is something I talked about it before. If you want to fuzz the method list.addItem, you probably first want to create the list and maybe also remove some elements from the list. So these sort of sequences, the static analysis cannot really determine that it makes sense to first call create and then add and then remove. But this is something that an LLM can kind of figure it out, especially if you pass to the LLM the documentation from the library. And that's something we do. So the LLM can figure out kind of sequences of semantically related APIs that make sense to call together. Also, as we mentioned, there could be multiple constructors to create objects in Rust. So we can use the LLM to select a set of constructors that are kind of heterogeneous enough to explore different code locations. Also, there are complications about traits because sometimes the function takes something that takes an argument that is of the must implement a trait, and this trait is implemented within the library itself. So we found out that static analysis was not very good at dealing with this, but on the other hand, LLMs are good at understanding this, or at least better than what we could achieve using static analysis. Okay, so this is kind of how we use the LLM. So we have statically generated harnesses. Then basically we pass them to this LLM with a proper prompt, try to improve them. And then, of course, LLMs not always give you correct code, but we can easily check if at least the code compiles. And if it doesn't compile, we can communicate the LLM the compilation error, and usually the LLM can kind of figure out what the problem is. Of course, you can repeat this loop maybe a few times, and then at the end you stop. But this sort of feedback loop helps a lot when dealing with LLMs. And then the validity checker also checks other properties about the code generated by the LLM, because, of course, we want, for instance, we want the code generated by the LLM not to contain unsafe code, because otherwise, if you have unsafe code in your harness, you might find a bug, but the bug is in the harness, it's not in the code you really want to fuzz. So we tell the LLM, do not include unsafe code, but sometimes the LLMs, they don't listen to you. So, but these are things that we can easily check statically, but just by parsing the code the LLM gave us. And again, if we don't like it, we ask the LLM to give us different code. And then we pass this back to the augmenter, and at the end, basically, we create a final corpus of harnesses that contains a mix of statically generated harnesses and also LLM generated harnesses. Okay, so I think I already mentioned most of these things. One thing I didn't mention, or maybe I just briefly mentioned, what we pass to the LLM is many things. We pass the originally statically generated harness, but we also pass, for instance, the documentation of the library, which can help the LLM to find semantically related APIs. But we also pass, I think, other static analysis metadata like the call graph. And then we also communicate what is the target API, and of course then kind of a quite long prompt about what the LLM should do and should not do. Okay, so here I'm just listing part of the prompt we are using. So we say you are a Rust code generation assistant. You need to find API of this. You need to fuzz API of this type. We will provide you a template of code. You kind of need to improve it, but do not completely destroy it. That's the point of what basically we are asking. And then we say, okay, we will also provide you other type of input files, and then after all this text, then we provide that information. And then we have a very long list again, a very long list of things that the LLM should do and things that the LLM should not do. As I mentioned before, do not use unsafe code, do not alter. Basically, a lot of these things are basically telling the LLM, do not modify some parts of the harness that we gave you, some parts that you need to keep them like them. Do not include comments, dead code, or unused variables. Or I think sometimes the LLM answers, but it answers like things like, here is your code, and then the code, right? But the part here is your code, you don't want it, because then you cannot compile that. So we try to convince the LLM to be responsible. Okay, and then as I mentioned, there is this validity checker. We do it, I think we try a bunch of times, but of course there is a maximum amount of tries, and if it fails, then we just go back to the statically generated harnesses. And what else? Okay, this I'm just showing an example of a automatically generated harness, and here the LLM figured out that it's a good idea to generate this DQ object using this constructor, and then this constructor, and then call I think this other. It can be, okay, here the LLM figures out that this DQ object can generate it using either this constructor new, but also this other method with capacity. And then it also figures out that you can call different operations on this DQ object. You can call pushback, popback. So this is kind of a queue. So it makes sense there are push and pop operation, shrink, reserve. And actually, by calling a specific sequence of these APIs, you can trigger a real-world bug in this real-world memory corruption bug in this library. So of course we did experiments. We evaluated this on a kind of large set of crates that are Rust libraries. We found I think we found 30 memory safety vulnerabilities that were already known, and also 12 new ones. So that's just to show that our approach works kind of on a large scale, and it can find both previously known bugs but also previously unknown bugs. Lessons learned. So in this case, LLMs are great at improving an existing fuzzing harness, but they are not so great at creating one from scratch. So one interesting thing about this project is that if you just provide the entire library to the LLM, or if you just ask the LLM create a fuzzing harness, it would not be that great. Similarly, if you only use static analysis, it would not be that great. But when you combine them, you get much better results. Of course, in the papers, we show all the data about this, but intuitively it makes sense, and we show it more empirically. Also, LLMs often produce incorrect code on their first attempt, but if you have a kind of a feedback loop and you communicate this feedback back to the LLM, then you can this procedure can eventually lead to good results. But of course, it's important to have to set up things in a way in which you can create such a feedback loop. Okay, and also LLMs are good at code generation, but they are not good at exploring all execution paths. So if you just give the entire code of these Rust libraries to the LLMs, and you ask the LLMs to find those bugs, it would probably fail in most of the cases, because the LLM cannot really reason too much about how to explore all these different code paths. But fortunately, we have fuzzers that are very good at exploring a lot of code paths dynamically by running the code very quickly. So in a sense, it makes a lot of sense to use LLMs to generate harnesses to help the fuzzer to then explore quickly all possible code paths within the code you want to test. And of course, we use this in the context of unsafe Rust code, but this sort of approach seems to be effective in general for program analysis. Okay, so just a few slides kind of to think about future ideas. So if you think about that, in this project, in the things I mentioned, we always use some LLMs. We use dynamic analysis such as fuzzing. We use some form of static code analysis. One direction in which research is going is to say, okay, but maybe we can still use these three things together, but we can use the LLM kind of as an agent, or we can use the LLM to orchestrate static and dynamic code analysis. And this is an approach that has been used by a few projects. Basically, what you can say, you can tell the LLM can be made aware of a list of tools that it can use, and then the LLM can output some text that says, okay, I want to use this tool to do this. And then you run that tool for the LLM, and then you communicate the results back to the LLM, and based on the results, the LLM can decide to maybe use another tool. And so the LLM can kind of orchestrate the usage of all these tools, and then at the end, reach a conclusion. So this seems to be an approach that works reasonably well for program analysis. This is probably an approach that works more in general, but a lot of research is going towards this direction. And indeed, this is kind of the approach that we use when we play a DARPA-sponsored competition called AI-XCC. And I'm not going to talk about it in this presentation, but all our code about that is public here, and there will be a paper on that. Okay, but still, people know that is kind of, or researchers know that this sort of agentic usage of LLMs could be a good idea, but of course, this is a very, very new field. There are a lot of open questions about how to efficiently query the LLM, or how to efficiently communicate large snippets of code to the LLM, how to get accurate results back from the LLM. The LLM sometimes tells you to do things that might violate some sort of safety properties. The LLM is definitely not that reliable. Maybe sometimes it answers correctly, sometimes it doesn't answer you correctly. So how to do all of these efficiently, accurately, safely, and reliably is unclear, and a lot of future work is underway in these directions. Okay, that's all for my talk. I can answer questions.
So we do have time for question. You want to start with that question that you...
Yeah, but I'm not sure I can see it. Okay. Can someone read it for me?
I don't see any online.
Okay. So we don't have online, right? We don't have questions online for now. Okay. Any question from the audience? Okay.
I have a question about static.
So you have to first wait so that your question...
I have a question on static harness generation.
Yeah.
Based on the example, it seems like it's focusing on generating a complex data type.
Yes.
Am I understanding correctly about it?
Yes, because that's one of the main complications of writing harnesses for Rust, is that if you want to call an API that takes as an argument a complex data type, you need to figure out how to write code to generate that complex data type automatically. Yeah.
Thanks. And I have another question.
Yeah.
Regarding the API sequence generation with LLM,
Yeah.
I remember some prior works on generating API sequence using traditional methods. have you considered that approach?
Yeah, so for Rust, there were some previous works on finding sequences that, in a way to kind of optimize code coverage, finding sequences that were exploring as much code as possible. But it was not very effective for at least the problems we wanted to solve. So maybe it can be effective in other cases, but in our case, it was not that effective. I think because in our case, it's not much of a code coverage problem, but it's mostly to reach some unsafe code and exercise as much as possible, but just that unsafe code and code related to it. So, but there were a few approaches purely based on static analysis, but we didn't find them very effective in our case. Yeah. Yeah.
Thank you for the great talk.
I guess you need to press something on.
Oh, this?
Keep pressing it.
Keep
Oh, hold it.
Okay.
Okay, great. So thank you for the talk. My question is, for the LLM of choice, was there a specific reason that DeepSeek was chosen? Is it because you can do it you can run it locally?
Yeah.
yeah.
So
Can you talk about that?
first of all, for the first projects I mentioned, we didn't use DeepSeek. We use other models. For the Rust project, we use DeepSeek. We also try other models. From our experience, whatever model you use, results are not that different. Of course, some models are larger than others, and so they are better than others typically. And some models are much more expensive than others. So for the Rust project, we actually also try with other models. And in the paper, we show that if you use models that have kind of more or less the same size of DeepSeek, you get more or less the same results. DeepSeek was quite cheap because you can use it from resellers, kind of that there's third parties that are hosting it in their own servers. But I think at the time that we ran the experiments, there was OpenAI 01, which probably it was better, but it was like 10 times or 20 times more expensive. So then, yeah, but I feel that, of course, if you want to switch model, you might need to change a few things. But I feel that all the research I presented is kind of not linked to a specific model. So maybe this is also lessons learned, that which specific model you are using does not matter that much. Yeah, of course, open models, they have some advantage, especially in the academic context, because you can do experiments that are at least more reproducible than instead using some commercial model that you might not even be able to access in the future, right? So yeah.
Yes, I have a question. Can I ask how fast we can use the LLM to generate the harness compared with the existing generated model, and what benefits we can get by leverage the LLM?
How fast?
Of the efficiency compared with the generated model, like the
Generative models such as
like the generated adversarial network, neural network.
Yeah, we didn't try that. We didn't try other machine learning approaches. We just try LLMs because I guess it was the easiest thing to do for us. I don't think speed was one of our main concerns, so I don't think it was particularly slow. We were much more concerned about cost because, you know, we pass to LLM a lot of information. Sometimes we pass the entire documentation of the library. No? So since you pay by tokens, that's kind of expensive. And the reason why we use LLM, I mean, I mentioned some reasons. Basically, there are things that are extremely hard to do with static analysis. There are things that are basically impossible to do with static analysis. For instance, determining sequences, determining meaningful sequences, like determining that if you have a list, you want to first create it, maybe add a bunch of items, then remove a bunch of items. if you just analyze the code, a human can understand this, and this is probably mentioned in natural language in the documentation, but it's not something that you can easily figure it out just by parsing the code, right? On the other hand, there might be comments in the code written in human language that can indicate it makes sense to do this and do that. So the LLM is good at analyzing those. Yeah. Can this research, okay, I see a question, but it's gone. Can this research project in fuzzing be used for other application other than low-level kernels? Well, the fuzzing research on Rust, we did not use it for kernel, but actually one potential future application is to use it to fuzz the Rust code that is slowly being introduced into the Linux kernel. More in general, yeah, I mean, I think using this combination of fuzzing, static analysis, and LLMs can be used in general to analyze any sort of code. In fact, for that AI XCC competition, we were also asked to analyze Java code, so more high-level code. Yeah.
I've got a couple questions from online. So one goes back to what you were just discussing. What is the biggest bottleneck in your current workflow, including LLMs? So your bottleneck in your workflow.
Well, it depends. I guess they are talking about the fuzzing project, or so. I mean, in fuzzing, fuzzing is a querying LLMs takes time, but I would say that the biggest bottleneck is still the fuzzing in itself. That when you do fuzzing, you need to run the code for maybe hours or days. And especially if you have a lot of harnesses, like hundreds of harnesses, then each harness you need to run it on maybe a couple of cores, and then, of course, you need a lot of computational power. Yeah.
Okay, yeah. The question was, in either of your projects that include LLMs or not LLMs.
So I think LLMs, of course, they take some time to ingest all the data you pass and to give an answer, but that's usually not the biggest bottleneck. Especially because you pay more, you get more, and so but the cost is an important consideration. Yeah.
Okay, another question about the PerSec lab. Are there any projects about securing LLMs against model inversion attacks and AI agent jailbreaking?
Yes, we have been doing projects on that. They can send me an email. I can maybe meet with them and discuss about potential projects. Yeah.
I guess, quite a lot of interesting questions. So let's thank the speaker again, and we can finish.
Thank you.